Hello Lockerbie. Today we're going to look at cooling curves and specific latent heat. So I love this experiment. Heat is required to change the state of a substance from a solid to a liquid. Conversely, when a substance changes from a liquid to a solid, heat is given out to the surroundings. We have two boiling tubes here, one containing water and the other containing stearic acid, and we've placed them in a beaker of water, which is then acting as a water bath. The beaker of water is heated to about 85 degrees Celsius, and then we're going to remove them like this, connect them to digital thermometers, place them in the rack, and we're going to just leave them to cool. So because they were in the water bath at about 85 degrees Celsius, the starting temperature of both of these boiling tubes with their contents was also at 85 degrees Celsius. You can see the temperature of both of these materials is cooling down. You can see that stearic acid is cooling down at a greater rate than the water, and that can be seen in the lines here. So as the water cools, heat is transferred to the surroundings, and the temperature of the water decreases with time, shown by the blue line on the graph. As the stearic acid cools, its temperature also falls and is represented on the graph by the red line. However, after a period of time, which is coming up now, you're going to suddenly notice that the temperature of the stearic acid remains the same. It's not dropping, it's not changing. The water continues to change its temperature and it continues to drop, but the stearic acid is staying at the same temperature. Now that temperature is hotter than its surroundings. If something is hotter than its surroundings, it is giving off heat. So this stearic acid is giving off heat to the surroundings. The question is, where is that heat coming from? It must be giving off heat. It's hotter than the surroundings, but its temperature isn't dropping. Well, the best way to think about that is to think about your molecular structure when in first year you first drew your pictures of a solid, a liquid and a gas. Now you see now the temperature of the stearic acid is beginning to drop again, and what's not really shown in this video is that if you did this for real, this stearic acid would have gone from a clear liquid to a sort of white, like compact snow solid in the boiling tube. So we've changed the state, and that's because at 68.5 degrees Celsius it reached its melting point or its freezing point. And heat is transferred to the surroundings because the stearic acid is solidifying. This hidden heat we call latent heat, and it's just transferred to the surroundings to warm up the surroundings. When all the stearic acid has solidified, the temperature of the solid starts to decrease again. Notice that we can determine the melting point of the stearic acid and the freezing point from the graph. So if we carried that across, we would have seen that that was about 68.5 as we found from our results. So this is a typical curve that you'd get of cooling. If this was water, we'd have this same shape, but this line here would obviously be flat at 0 degrees Celsius because that's the freezing point and the melting point of water. So we're now going to look at latent heat, and we're going to start with latent heat of fusion. So when we heat a substance, the temperature doesn't always rise. We need to supply heat to change a solid into a liquid or a liquid into a vapor. These changes occur at the melting point and the boiling point. So a solid to a liquid occurs at the melting point or the freezing point, and the liquid to a vapor happens at the boiling point. And I'm sure that you know that for water, those two temperatures will be 0 degrees Celsius and 100 degrees Celsius. That's what the Celsius scale is dependent on. So what we've got in this animation here is we are going to find a method of measuring how much heat is required to melt a substance. And in this case, we're going to be melting ice or water going to change the water from its solid phase into its liquid phase. Now we've only got half a kilo here, half a kilogram. That will be mentioned again. Now again, this has been lagged. We would expect this to be lagged at the top as well, so that any heat energy we're adding is staying in the water and we're not heating the surroundings. In reality, there would be some heat lost to the surroundings. So we're going to switch that on and leave that running. And we'll keep going. So this is going to automatically switch off after half a kilogram of ice has melted. You'll see that the temperature is at 0 degrees Celsius, and that's really important. We're not having to heat the ice up before it can melt. You can see here that the level of the water is rising as the ice begins to melt. So we're getting less ice and we're getting it's becoming water. What's very fascinating is we don't melt a little bit of ice and then heat that up. We melt all the ice and then the temperature starts to change. So the heat to melt 1 kilogram of ice is going to be twice the energy that it's going to take to heat half a kilogram of ice. And that's what we call the specific latent heat, because the specific latent heat refers to a mass of 1 kilogram. And you've got two different types of latent heat. We've got latent heat, specific latent heat of fusion, which is ice melting, and specific latent heat of fusion, which is the melting, and specific latent heat of vaporization, which is turning a substance from a liquid into a gas. So the definition of that, it says here, and I prefer you to use the one I'm going to say, that the specific latent heat of fusion of a material is the heat required to change 1 kilogram of a material from a solid to a liquid without a change in temperature, or as it says here, at the melting point. So it isn't any energy to change its temperature, it is only to melt the substance. In this case, we've got 167 kilojoules to melt half a kilogram. So if you double that, you'll end up with a specific latent heat of fusion for water as 3.34 times 10 to the 5. And the units here, joules per kilogram. There's no degrees Celsius, there's no Kelvin on that one, because we're not changing the temperature. The formula is EH equals ml. It's a standard formula. What you can often do is put a little F for subscript for latent heat of fusion, or a little V after the L for latent heat of vaporization. So here we've done the specific latent heat of fusion, and it is the heat energy required to change 1 kilogram of a substance from a solid to a liquid at the melting point. Something else that's important, it would also be the energy given out when we changed 1 kilogram of a material from a liquid to a solid at the melting point or without a change in temperature, which is what we did with our cooling curve. So let's have a look at the specific latent heat of vaporization. So in this case, what we're going to do is we're going to be looking at how we would change a liquid into a gas, and that's the energy required to do that. Here we've got a balance, and on top of the balance we've got 2.5 kilograms of water. We've got a little heater heating it up. We've lagged the beaker as well, got a temperature probe. When you do this in the lab for real, it's a lot more difficult than it's shown here. The balance is obviously the water is going to be boiling away, so it's obviously that temperature was already meant to be at 100, and we're going to have to wait until the mass reading on the balance says 2.5 kilograms. And then we know that we've boiled away half a kilogram of water. There's a few things for this experiment. If any of the gaseous water hits on the wires or the sides of the container, it's going to drip back in to the beaker. So you're going to have to reheat it. So that's going to give an overestimate for the energy required. And also when you do this experiment, it can splash. So big sort of lumps of water sort of splash out the beaker, and that will give you an underestimate of the energy required. So it's dropping nicely there. So the heat energy to vaporize 1 kilogram of water is going to be twice the value that we're going to get. I'm really hoping that you would think and be able to work out which is going to require more energy. I think it's going to require more energy to boil or vaporize 1 kilogram of a substance, or change it from a solid to a liquid, or melting 1 kilogram. Look at that little diagram you did in first year of your solid, liquid and gas. You would appreciate that it's going to take a lot more energy to turn a substance from a liquid into a gas than it would to turn it from a solid to a liquid. And that's because you're sort of having to rip apart those close bonds between your solid, your liquid, and your liquid and your gas. So the specific latent heat of vaporization of a material is the heat energy required to change 1 kilogram of the material from a liquid to a gas without a change in temperature, or at the boiling point. So there's a mistake there. So it would be the specific latent heat of vaporization of a material is the heat energy required to change 1 kilogram of the material from a liquid to a gas at the boiling point, or better still say, without a change in temperature. You can see that it's still going. We've lost there 0.45 kilograms of water we've boiled away, and already we've used more energy than we did when we worked out the specific latent heat of fusion of water. So we're going to use more heat energy to do that. So this is for half a kilogram, which is 1,130 kilojoules. So if we double that, that's going to be 2,260 kilojoules, which gives us the specific latent heat of vaporization of water as 2.26 times 10 to the 6 joules per kilogram, or 22.6 times 10 to the 5 joules per kilogram. So it's much greater than the energy required to melt 1 kilogram of water, which is why you shouldn't have your kettle overfilled, because the energy to boil 2 cups of water compared to boiling 1 cup of water is a lot greater. So that gives us again the formula EH equals ml. So you can either use this as the formula for both of those equations, or you can put the little v and the little f to show you whether it's specific latent heat of vaporization, specific latent heat of fusion. You'll find the values for this in your data sheet on page 2 of the exam paper. So here's an example that we've got. Calculate the heat required to change 2 kilograms of ice at 0 degrees Celsius to water at 0 degrees Celsius. So there's no change in temperature. We're just melting this ice. So we've got the formula EH equals mLF, where LF is the specific latent heat of fusion of water. Your mass is 2 kilograms. The specific latent heat of fusion of water is 3.34 times 10 to the 5 joules per kilogram. Multiply those together, and that gives us 6.7 times 10 to the 5 joules. On part B, we're changing 0.6 kilograms of water at 100 degrees Celsius to steam at 100 degrees Celsius. So again, no change in temperature. Same formula, EH equals mLV, where LV is the specific latent heat of vaporization of water, which is your 22.6 times 10 to the 5 joules per kilogram. Multiply that by your mass, and you get a whopping 1.4 megajoules. So notice that the specific latent heat of vaporization is much larger than the specific latent heat of fusion, and we've discussed why already. So all that's left is an interactive summary for this section. Temperature is a measure of the hotness or coldness of an object. Different materials need different quantities of heat to change their temperature by 1 degree Celsius. Specific heat capacity is the heat required to raise the temperature of 1 kilogram of a material by 1 degree Celsius, or 1 Kelvin. The unit of specific heat capacity is joules, and remember that should either be in brackets, so joules per brackets, kilograms, degrees Celsius, or better still, joules, kilograms to the -1, degrees Celsius to the -1, or joules, kilograms to the -1, Kelvin to the -1. The specific latent heat of fusion is the heat required to change 1 kilogram of the material from a solid to a liquid at the melting point. Heat is needed to change a liquid into a gas. When a volatile liquid such as perfume evaporates from the skin, the heat needed to do this is taken from the skin, which then leaves the skin feeling cold. Thank you.